Yo, guys, so today got some questions on periodic properties. Whoops. So what I'm gonna do today was supposed to be bio cells and stuff, but I did that yesterday and I don't remember anything that I learned. I did this one today, so what I'm thinking I'm gonna do is like I'm gonna review the topics that I learned the day of, rather than doing it the next day, because I genuinely don't remember what I learned yesterday. So I need to do some more studying for that. But this is what I learned today: periodic properties. So hopefully things go well. Now, how do we start this? What do we? Wait, let me just. Wait one sec. Okay. What is a group and what is a period? What is common within each? So a group goes down, so those are columns. A period is a row. Periods, they have the number of energy levels common. The group has the number of valence electrons common. So what does it mean by valence electrons? It's just the outermost shell. They'll have like the same number, because if you're like trying to fill in like those 6 electrons, they'll have like the same number at the very end. Like if you look at a periodic table, what's the atomic number? The atomic number is the number of protons. What are the group 6? What are 6 group names? Well, first of all, there's earth metals. There's not earth metals, alkali metals. Then there's alkaline earth metals. Then there's transition metals. Then there are the metalloids. There are also the post-transition metals. Maybe post-transition metals go before the metalloids. After the metalloids, we have. Oh wait, let me just tell you the group. So group number 1 is alkaline metals. Group number 2 is alkaline earth metals. Group number 3 to 13 or 3 to 12 is transition metals. Then group 13 to 15 are the post transitions. Then in between there we have like the metalloids, which are on the staircase. Group 17 we have the halogens. Group 18 we have the noble gases. And yeah, there's like non-metals in between, but I don't think those really count. What are the transition metals special and why does it happen? Well, transition metals have multiple oxidation states. They don't have one specific one, they just have multiple. Why does it happen? That's a good question, actually. I'm not too sure why. Let me look at this. Oh wait, can't forget about the lanthanides and the actinides. Lanthanides and actinides are down there, but usually transition metals have a oxidation state of +3. The transition metals, they go from +2 to +7. So yeah, wait, where's the multiple? They have this property because they have several electrons with similar energy. Okay, so the reason that transition metals, let me just write this down. Transition metals, what is unique about them? Why does this happen? Multiple oxidation states have several E- with similar energies. Okay. Done. What are the inner transition metals? Those are the lanthanides and actinides. Yeah, lanthanides and actinides. Is there anything I need to talk about them? What are they called? What is the common charge? Common charge is +3, I'm pretty sure. What makes them unique, they also have they fill in the F orbital, which is N-2, I believe. But I don't really think they're going to look at that. What are diatomic atoms? The diatomic atoms are just atoms that naturally exist with, they're just elements that exist with 2 atoms. Diatomic atoms include, what is it like? Don't be scared of cold beer. I have it here. Have no fear of ice cold beer. So there's H2, have no. So there's N2, have no. There's F2, no fear. O2, F2. Wait, no, F2. Have no fear of ice cold beer. Have H2N2O2 F2 I2 Cl2. Have no fear of ice cold beer. So H2N2O2 F2 I2 Cl2. Oh, and Br2. I forgot about that one. 6 qualities of metals and non-metals. Okay, well, bro, what? Okay, so metals are malleable and ductile. That means like they can roll up together and stuff like that. Like they can be stretched out. Metals, they form basic oxides. Metals, they have a higher boiling point and melting point. Metals conduct electricity. What else? Oh, wait. Okay, wait. So to go back, what is the common charge of the transition metals? These are +2. Then lanthanides and actinides, they're +3. Okay. So anyways, going back to the qualities of non-metals and metals. So metals, they are malleable and... Wait. Malleable? Is ductile the same as lustrous? Okay. So there's actually 3. Damn, what kind of car is that? It's a Mustang. Oh, why is it got parked up? Damn. Okay, wait, let me lock in. 6 qualities of metals and non-metals. So they're malleable, ductile, and lustrous. Lustrous means that they're shiny. Malleable means that they could be rolled into sheets, and ductile means they could be put into wires. Metals form basic oxides. Metals are conductive of electricity. They have a higher melting point and boiling point. But what are the other ones? Why can't I think of these, bro? Okay, let me just look. Okay, so they lose electrons to form cations, and then they're usually solid at room temperature. Then there's the exception of mercury being liquid. Okay, now what are the properties of non-metals? Non-metals form acidic oxides. They are brittle, dull, etc. They do not conduct electricity well. They form anions because they lose electrons. No, they form anions because they gain electrons, bro. What am I saying, bro? They gain anions because they gain electrons. But why am I low-key struggling with this? They got low boiling points and melting points, and then they are normally gas at room temperature except bromine, which is liquid. Okay, that's done. Okay, what is atomic radius? That's just the distance between two atoms' nucleus. What is the trend across group and period? Wait, atomic radius. Did I even say that right? Atomic radius is like the space between the center of atom to the end, right? Yo, there's no way I'm tweaking over atomic radius. Half the distance between the nuclei of two identical atoms bonded together. That's literally what I said first. So the radius would be larger if the thing is larger. Okay, that makes sense. Okay, what is atomic radius? What's the trend? So as you go across a period, you're going to see a smaller atomic radius. Now, why is that? Atomic radius will decrease because the atomic number will increase as you go from left to right. That means it has a higher positive charge, so then the electrons are more tightly held. Now so like it's just like the opposite for like going the opposite direction. Like if you go from right to left, it's gonna increase atomic size because the electrons will be held less tightly. As you go down a group, the atomic radius will increase because you're gonna have more shells of electrons that are adding to like the clunk of the atom. As you go up, there's gonna be less of shells, like less energy levels of electrons. So it's like it'll be smaller. Also, like less shielding and stuff like that. Define effective nuclear charge. What is the equation? What is the trend? So a nuclear charge normally is just like like we got the proton and it's attracted to the electron, and that's just like the nuclear charge. Now, effective nuclear charge, that's taking into account the inner shielding electrons. So like if you have like the proton in the center, and then you got electrons on like the sides, right, like orbiting around, the inner orbital electrons are gonna kind of push away the outer electrons. It's gonna because those inner electrons are gonna block that force that the positive core is trying to like put out, and also the negative like charges like repel, like the negative charge and the negative charge will kind of repel, but that's like not really relevant to this case. What is the equation? The equation is the atomic number or number of protons minus the non-valence electrons, in other words the shielding electrons. Why? I don't know. What do you mean why? Like what do you mean why does it happen? What is the trend? Oh, that's what that's. What is the trend? So as you go from left to right, atomic number increases. That means you got a higher number of protons. That means you got higher like attraction. So that means the Z effective will increase going from left to right of a group period. Now going down a group, the ZF will decrease because you're gonna have more inner shells of electrons. You have more energy levels in between the valence electrons and the nucleus. Bro, I had an organic chem, bro. Like, this is kind of side tangent, but bro, I finished like with not that good of a grade in organic chem. Like, sure, it's like decent, but I'm not happy with it at all, bro. Like, I was doing good over the semester. I had a 97 in my lab portion, right? And then I got the lab exam, bro, and it's like, bro, like it's just like we get assigned like a random lab throughout the semester that we did. And like, bro, some people, all they had to do was sort of like distilled fractionation. Some people had like simple distillation or something like that, And like, bro, I swear my lab group, like we genuinely got like cooked, bro. Like it's just so much shit we had to do within like 50 minutes. And it was just so ambiguous as to what we did. And that tanked my lab grade, bro. If I finished with at least like a 95 in my lab grade, I would have gotten a way better mark than I wanted on my thing in my like overall, bro. But now it's like I'm just so mad, bro. But anyways, what does isoelectronic mean? That just means you have the same number of electrons. So it's like if you look at a periodic table, it's like, so if you have potassium, right, which is period 4, if we lose an electron, we're going to jump over to the same electron configuration as argon. So the term isoelectronic just means like if you're like in an isoelectronic series, that means you have like the same kind of electron configuration. If you take away an electron from potassium and you get K+, that's isoelectronic with argon, because removing one electron from the valence shell of potassium, that will result in a fully stable octet being left behind, and that's isoelectronic, or like same configuration as argon. 2.3, what is the ionization energy and what is the trend? Ionization energy is when you remove, like how much energy does it take to remove an electron? Let me just fact check. I saw like some different so the energy required to remove an electron. So Again, what is the trend? So if we like got a group, as we go down a group, it'll require less energy to remove an electron that is way farther from the proton or the nucleus, because like, okay, wait, let me just start. So if we start like near the top of the group, like fluorine area, like period 1, like period 2, period 3, like etc., right? That has like barely any inner shells, right? But if you go all the way down, right, like to the very bottom, like I don't even know what the bottom is, but if you go to the bottom, it's gonna have like so many like inner shells, right? So because those inner shells and because of all that shielding going on, then it'll be easier to remove that last valence shell, that last valence electron, because it's going to be having less attraction to the inner, like the nucleus, right? If you have like one closer, like with less energy levels in between, like less like shielding levels in between, then it'll be much harder, because the electron that you're trying to take out is much closer to the proton than something like that has like many shells in between, you know what I'm saying? So that's kind of like what it means. So and then going from like the other way, like going across a period, so if you go to the right, from left to right, ionization energy will increase. Again, similar reasons to like ZF and stuff like that. You got higher atomic number, higher proton, higher like higher number of protons, which means higher attraction towards those electrons that you're trying to remove, so it'll just be harder, etc. So, why would I even say etc.? What do the values of subsequent ionization energies compare to the first? So subsequent ionization energies, those will always be higher than the first one. Why? Because, well, like I don't really know why. It doesn't really make sense to me. Like what I don't understand, right, is if you take like magnesium, removing magnesium, because magnesium is going to have a full 3s2 orbital, right? Now if you remove an electron from that, that's like a filled orbital, right? So it'd be hard to take it out. But now going from a 4s2 to 4s1, like I'm going from 4s1 to like a 4s0 or whatever, that should be easier, right? Because it's half filled. You know what I'm saying? It's like, what's that even mean? I don't know. I'm gonna read it. I'm gonna learn it. The first ionization energy is the energy required to remove the outermost electron. Following the removal of the first electron, elements can have second, fourth, etc. The energy associated with removing each successive electron increases. Okay, so it's talking about sodium. Bro, what? Okay, that's like, bro, I don't even get that. So is it always just going to be higher? It's just like I just memorized that, but I don't understand why. Like why, bro? Why, bro? Why? Why, bro? Why did that happen? Why? That's something I need to talk to GPT about, or Gemini, or Claude, etc. Bro, I just keep on talking, etc. Like, etc. this, etc. that. Like, bro, what that? What are the two notable exceptions to ionization energy trends? Why? Okay, so something to note. So I'm looking at the periodic table right now. Group 13 will have a lower ionization energy than group 2. Is that right? Yeah. Group 13 elements like boron, aluminum will have a lower ionization energy than group 2 alkaline earth metals like beryllium and magnesium. Why? Well, boron, to go to, so like, you know how we got like the energy levels, right? Like we got 2s2 and then we got 2p2. Wait, no, spdf, sp. So 2s2, is it 2p2? Well, I don't even remember how you do that shit, bro. 2s2, 2p2. But anyways, so we have 2s2, which is filled, and then we have one electron in the That's the P, right? P, bro. There's no way I don't remember this, bro. But anyways, we only have one electron in the p orbital. So in order to remove that, that's like easier to remove in order to get to like the 2s2, because only one electron, like it's like not stable, like you only got one electron there, it's like you don't care, like you could just like let it leave, you know, it's not that deep. But now beryllium, on the other hand, it has a full 2s2 orbital. So if you want to remove that first electron, that's going to require a lot of energy, because it's already stable. It's already in a filled orbital, and filled orbitals are stable. So if you try removing that one electron from that filled orbital, it's going to cause some problems. While for boron, if you remove one electron, it ain't going to care, because it's going to land in the 2s2. While you only got like one electron in the p orbital, it's like it's not going to matter. So basically, that's one exemption. Another exemption is, oh yeah, group 15 and 16. So kind of similar to what I was saying before. If you look at nitrogen and you look at oxygen, just some examples of group 15, group 16. Group 15, nitrogen, that's going to be 2s2, 2p3. So it's going to have a half-filled orbital, like half-filled p orbital, that is relatively stable. Half-filled and filled orbitals are stable. Like half-filled are less stable than fully filled, but fully filled, what did I even say about fully full? I don't know, but anyways, the point I'm trying to say is nitrogen, to remove one electron from that half-filled stable orbital, it's going to require more energy than just trying to remove one electron from the 2p4 of oxygen. Like, you know, like, because removing the fourth electron from the p orbital for oxygen, that's chill, bro. Because if you remove it, it'll result in a stable half-filled orbital. But for nitrogen, if you try removing one, that's like disrupting that stable orbital, and that's going to cause some problems. So that's why group 16 ionization energy is less than group 15 ionization energy. Theoretically, according to the trend, the oxygen should have had a higher ionization energy compared to nitrogen, but it doesn't. So yeah, briefly, the two exceptions are group 13 and alkaline earth metals, and then group 16 and group 15. So yeah, basically, technically. Okay, so electron affinity. This is the last part. Damn, this is tiring, bro. I gotta review that cell stuff tomorrow, for sure. What is electron affinity? Electron affinity is the amount of energy released when an electron is gained. What is the general trend and why? Well, bro, it's the exact same as everything else that we learned, except atomic radius. Electron affinity increases as you go across from left to right on a period, and it increases from going like down to up on a group. That makes sense, right? Like, yeah. So what is electron affinity? Okay, so why is it that case? Well, more energy will be released when you add an electron to like something that it wants to. Like, you know, if you add, like, you know, with like fluorine, you know, it's like super attracted to adding an electron, because, you know, it's like high positive charge, low number of inner shells. I think that's the right term. So it's going to be like, yo, I want this electron. So then adding an electron will release a lot of energy, because it's like, I want this. And then when it gets it, it'll release energy. So that's basically why. Like, taking, like, if you look at iodine has a larger proton, like a higher number of protons, but it has a lot of shells in between the valence electron and the proton. So adding one electron to iodine, because it's like already shielded by so many, it's gonna be like, oh, I got an electron. Well, for me, like, oh, I got an electron. So it's gonna be like, shit, like I got like release all this energy, like, you know what I'm saying? So that's basically what it is. What are the two exceptions to electron affinity? I think something had to do with the noble gases. Like, noble gases will not do this. Like, electron affinity is 0 for them, because they're not going to want to do anything. What's the other one? How do I not remember this, bro? This should be common sense. Oh, there's three exceptions. I wrote that wrong. So it's the exact same as ionization energy. Let me try explaining it. So we got the electron affinity. So the general trend is for it to increase going from left to right. Now, so relating back to the previous one, group 15 element will have a lower ionization energy. Lower electron affinity because they're already stable with their half-filled orbitals. So it's like, I don't really need another electron. So that's why they don't want to add it. And like I said, noble gases, they're already filled. So it's like, why would I want anything else? Then the other one is the 4s2. Like the S2, like when you fill the S2, it's like, bro, like you're already stable with a filled orbital. It's like, yeah, I don't need another one. Like I'm chill with where I'm at right now. So that's like the other exception. What is electronegativity? That's just the relative ability, like it's just the ability, like the desire of electrons for an atom. So fluorine's the highest, then the bottom left is the least. What and why is the trend? Well, kind of relating back to everything that I've been saying, like over and over and over again. Fluorine, top right, that has the highest proton charge with the least number of inner shielding electron levels. So it's going to be like, yo, I want an electron, I want an electron, I want an electron, I want an electron. But then like the bottom left, that has the lowest number, like that has like a low number of protons and a very high number of okay, if like francium or whatever, that has a lot of protons, but it still has a lot of shielding electrons in between. So that's why it's like the lowest electronegative atom. So yeah, so that's basically it. What is the brief recap of trends? Well, we got atomic size. Atomic size decreases from left to right and increases going down. So it's just like an arrow going to the bottom left. The second one that we talked about was ionization energy, I think. How did I forget about ionization energy? Okay, let's talk about ionization energy. Ionization energy is just the energy released from the energy required to remove an electron. So that's like, it increases going, like, it's like the same trend as electronegativity, it just makes sense. Then there's ZF, same thing for the same reasons. There's electron affinity, same thing for the same reasons. And electronegativity, which is the same thing for everything. So yeah, that's basically it. I'll see you tomorrow.